Okay, so here's our first kind of introduction to physics, but the first thing we're going to learn is about proper measurement techniques, and we learned this in Chem 1, so I think it's going to feel familiar to us, but there's a couple little taglines that I need to remind you of when we're taking measurements. So let's get into a little introduction first. In physics, we use math kind of as our language, and we're going to get a whole equation sheet, okay? You're going to make your own equation sheet as the year goes on that you'll always get to use. Okay, so I let you use your equations on quizzes and tests, things like that. So you'll make your equation sheet as we get into it a little bit. And so we use those equations just to help us figure out what are we trying to solve for, right? And help us do the math to go there. So these are some things that we need to think about in terms of our math skills. Can you rearrange an equation to solve for an unknown variable, right? So let me just throw up one of our equations here. Let's say this is one of our initial equations. VF squared equals VI squared plus 2A delta X. Okay, you don't have to write this one down. I just want to see how would we rearrange this? Let's say that I wanted to solve for final velocity, right? My goal was to solve for VF. Actually, I didn't pick a very good one. You don't have to rearrange that. Let's say I wanted to solve for VI. Okay, if I wanted to solve for VI, any thoughts about how we could get there? What would I have to do? Yeah, just say it out loud. You don't have to raise your hands. Fine. Tell me what you think. Okay, I got to isolate. I got to get by itself. So what am I going to do to this whole term right here? Subtract it over. So minus 2A delta X. So now we're at VF squared minus 2A delta X equals VI squared. And so now where am I going from there? I have to square root both sides. Okay? I think it's easier to do that with numbers plugged in, right? If it were me, I would solve whatever number that is and then move it over, right? But that's what you have to be comfortable with, is figuring out what system of equations or what solving equations method works for you. For me, I much prefer to solve it with numbers in first. Yeah. So that'll be something that you decide on as you go through. So can you rearrange and can you solve for a variable? Can you plug in numbers for multiple variables in an equation? So like this equation I showed you here, we have, 1, 2, 3, 4 different variables. Do you know what I mean when I say the word variable? Right? It's a letter that represents some value. And so VF stands for final velocity, initial velocity. A, any guesses? Acceleration, and X stands for distance or displacement. So in this problem, we're studying all of these things together, but we have to be able to pick those numbers out of the problem, right? Typically based on their units, but we need to know that if something's measured in meters, it's probably going to go in for my distance or my displacement variable. Does that make sense? We're going to have to feel really comfortable with that. And we start real small with equations and simple problems, but then they get kind of complex, right? So we have to be able to put things in where they need to go. Okay, so those are the types of questions you need to be able to ask yourself about the math part. A majority of our work in physics is in the form of a word problem. So some people hate word problems, I get it, but I'm going to give you some kind of tactics for how we solve that. We always are going to write down what we know. It's really important that we make a list in the margins usually of what we are solving for. So again, if I'm reading the problem and I see, my velocity is 5, my acceleration is 4, my displacement is 12, right? I'm going to make a list of that for myself. And if it asks for the time, I might say there's my question mark, right? This is what I'm solving for. And so by knowing that information, I'm allowed to go then check my equation sheet and figure out, okay, what equation do I have that has velocity and acceleration and displacement and time, right? And so that gives me kind of a way to focus my search for the right equation. Does that make sense? Okay, so I'm going to strongly recommend that. You will always see me do that for problems. I always make a list. So it'll keep me a little more organized. All right, what an equation should be using. Typically, I'll write the equation out with just the variables first to figure out what it is. And then I'm going to find out what should I solve for. I'm going to plug in the numbers and solve. Okay, I like to plug in numbers Once I know what equation I'm using, I like to plug in numbers and get it going. Okay, I don't like to rearrange the equation with variables. So that's really up to you, but yeah. Okay. Some things that you need to ask yourself: does your answer make sense? Is it a reasonable number? Right. I'll give you a little caveat of that. Sometimes when I make up problems just to do in class, they don't always make sense because I'm just making up numbers. But most of the time, our numbers should make sense, right? They should be reasonable values. So you kind of have to check that. And do you have the correct units on your answer? So we're going to talk a lot about assigning units to correct variables and things like that. So we want to make sure that we look on that every time we do problems, especially on assessments. Okay? So there's our little intro into math. And so now we're going to review here how we take measurements correctly. Okay? We need to understand that a measurement is just used to quantify my observation. What do I mean when I say quantify? What's that prefix quant mean? Usually means a number, right? Quantity, whatever. Okay, so when we say we want to quantify an observation, that means we just want to put a number to our observation. So things like mass, volume, length, all of those are quantities. They are quantitative forms of data or observations. And so when we take measurements, we're trying to put a number to our observation. We're not just going to say, it's pretty long. We're going to say exactly how long it is, right? When we take observations or take measurements, it's really important. This is our tagline that I want you to remember, okay? We're going to read what the instrument gives you and estimate one more digit. Estimate one more digit. That's the really, really important part, okay? And so we've talked about this in previous examples, but I want to give a little bit of a sample here. So let's say that I have a ruler. I'm going to zoom in here on a ruler. This is 15 centimeters. This is 16 centimeters. So that means that's half. Okay, they're not perfect, but not too bad. Okay, so let's say I'm measuring something that goes to here. Okay, if I'm going to give a correct measurement, I have got to see where does this end up on my ruler. Where does it end up? Okay, so I'm going to take a look at, we say it's somewhere probably about here. Okay, so luckily for me, I can draw on it, right? So it ends up somewhere around right here. When I read what the instrument gives me, that means I know it's between 15 and 16. Agreed? So I'm going to say it's 15 point what? 15.6 something. I know it's between 15.6 and 15.7. Agreed? That I know for sure. So that's me reading what the instrument gave me. Now I've got to estimate one more digit and figure out where does it fall between 15.6 and 15.7. So what would you put it? What value would you put there? 15.6, 8. I would maybe say 7. You could go anywhere between 15.66 and 15.68, and I think you'd be fine, right? Because it's just an estimate. So there's really no right or wrong, but we're just estimating. So that's what I would put, okay? And so that's my final unit there. So when we have these measurements, we know that that last digit is estimated, okay? So that applies to all types of actual measurements we take in the lab, not digital measurements. Obviously, you're not adding a number to a stopwatch, right, or a digital scale. But anytime we go back there and use a ruler or a triple beam balance or a graduated cylinder, those are what we're going to practice with today. You have to figure out what's it measured to, and then how can I estimate one more digit, okay? Let's take this one more time here on a ruler example. All right, let's say that this was not 15 and 16. Let's say now that this is 10 and 20. Okay, so we're zooming it out a little bit. And let's say that whatever we're measuring is right there. Okay, so now if I'm going to read that measurement, I know it's between what? What two things? This is 11, 12, 13, 14, 15. So I know it's between 13 and 14, right? So that's reading what the instrument gives me. 13 point, and then I get to estimate one digit there. So where would we put that? Yeah, 13.6, right? Unfortunately, you're not gonna have the ability to zoom in like this on what you're doing in the lab. So you just have to take your best guess, 13.6. We call this centimeters again. So I didn't get to do two decimals here. I didn't get to say 13.60. I just got to estimate one digit because what I knew was that it was between 13 and 14, and then I estimated one more. Okay? Before we go back to the lab and do our measurement stuff, I want to remind us when we measure with a graduated cylinder, that's the tall, skinny glassware, right? And it has water in it. If here's my water in there, do we measure from the top of that curve or the bottom of that curve? The bottom. Do you remember what that curved line is called? It's also in your knee, the meniscus. Okay, so we measure from the bottom of that meniscus, which in our glassware is kind of difficult because it's so small. So you really have to make sure you're at eye level. And you can see there's kind of a shadow on the meniscus normally, but you have to really make sure you're at eye level because if you're above it, it looks totally different than when you actually get to eye level. So just make sure that we're good with that. Okay. Measurements are evaluated using precision and accuracy. Accuracy means how close they are to the actual value. Okay, I like to think accuracy is close to actual. Okay, so it's how close we are to the actual value. Precision is how close together our measurements are to each other. So it's kind of the range. Okay, so a lot of times we like to visualize this on a target. I don't know which one I'm looking for. Here we go. Okay, I can't draw it on here. I don't know how. Okay, but if I have a target, and I've got a bunch of attempts there, are my attempts accurate or precise, or neither? They're not really either, are they? Right? We have one accurate attempt, right? One bullseye, but they're not, I wouldn't say that's a good group of data collection, right? If we're using this analogy. If my attempts were all right here, what would that be considered? Precise, but not accurate, right? They are precise. They're really close together, but they're really not close to the actual value. So we're really close, but this would be me like reading the meter stick wrong, right? I think it's 62, but it's actually 67, right? It's on the other side of the 5 mark, and I'm reading it wrong. I might be reading it wrong consistently, so I get really precise measurements, but not really accurate measurements. So just something to think about. We want to try to evaluate our measurements as both being accurate and precise. Okay, I'm not going to talk about that. Okay, or that either. Kilogram for mass, second. And then the other ones we don't really use in physics. So the top 3 are what we really need to pay attention to. Kelvin we do every once in a while when we're talking about temperature. Moles really applies more to chemistry. Amps, it does apply to physics, but we just don't get to the electrical current study. And then candela is luminous intensity, right? How bright the light is. We don't typically get to that either, but these 3 are our main focus. Do you see one here that stands out as different than the others? One of them to me stands out. No, because it has a prefix. Yeah, right? Why is it not just gram? Right? It's kilogram. Why is it not gram? The answer to that is So gram is the unit for mass, right? That's the middleman unit for mass. But they use kilogram as their base unit because grams are so small. And if we measured everything in grams, it would be thousands of grams every time. So instead of having to say something is 12,400 grams, right? They can say it's 12.4 kilograms. So it just makes our numbers a little bit easier to work with. So that's the one that I think stands out a little bit, but that's that. Here is our metric system conversion chart. Do we remember this somewhat? Yeah. Okay. I have bigger copies of this if we feel like we need one at some point. I'm not going to get it out today, but I can give you a bigger copy of that rather than the slide in your handout. But all of these prefixes apply to every set of units. So this right here in our chart is where grams goes, or meters, or seconds, or whatever it might be. All of those things fit in that middleman. So if I asked you how many centigrams are in a gram, what would you tell me? How many centigrams are in a gram? 100, right? 100, because centi is 100. Okay? I much prefer giving the larger unit the 1. I don't like dealing with decimal versions of it. It just doesn't, I don't like that. Okay, so I like to always give the bigger unit the 1 and go from there. So I'll give you a different chart of that if you need later. Up. Here is our conversion between US and the metric system. Even here, I probably like to do this. 3.28 feet is equal to 1 meter because I like to give the bigger unit the 1, right? That's my preference. So here and here, I could technically change it. 2.2 pounds is equal to 1 kilogram, right? If you want to have the larger unit get the 1 there so you don't have to deal with any decimals. Every chart kind of has them built in differently, but I prefer that the unit that is larger to get the 1. That's my preference, but you can do lots of different ways. Okay. We're going to do just a couple unit conversion practice here, and we'll see how good we feel about remembering unit conversions. Okay. This says Ty ran 2.433 kilometers. How many centimeters did he run, and how many miles did he run? So before we even really dive into doing the math part of it, if I'm talking about how many centimeters he ran, is that going to be a large number or a small number? It's going to be really large. He ran 2.4 kilometers. So that's over a mile, right? So that means that's a lot of centimeters. So we're going to expect a big number here. Luckily, converting in the metric system is super simple, right? Because everything's on a scale of 1 and 10 and 100 and 1,000, right? So I'm going to start with what I know, 2.433 kilometers. I'm going to put it in my chart. Kilometers. Can I go directly kilometers to centimeters? Do I know how many centimeters are in a kilometer? No. I don't. Off the top of my head, I don't. I could figure it out, but I don't want to. Then I'm going to go meters to centimeters, right? Meters is our middleman. So that's what I'm going to do. And then I just got to fill in the math, fill in the numbers. Does it look like this? 1 meter is 1,000 kilometers. It's the other way around. Other way around. That's really something that people trip on a lot. 1 kilometer is 1,000 meters. I think we know that kilo means 1,000. A lot of us know that, but then we get it mixed up the wrong way. So we're going to go the other way. 100. So that means we ran 243,000 centimeters. Okay, you can plug it into your calculator, but how many of us feel good about moving the decimal place? Right? This tells me I need to move it 3, 1, 2, 3. This tells me I need to move it 2 more, 1, 2. That's how I came up with that number a little bit quicker. Okay, you can still plug it into your calculator, no problem. So that is how many centimeters he ran. Then now it asks how many miles did he run? Are we expecting a large number here or a small number? A fairly small, right? Fairly small. I probably am just going to go ahead and start back at what we know. Because what if I did this number wrong and I try to convert that to miles and now I'm wrong twice, right? So I'd start with what we knew originally, 2.433 kilometers. You could go kilometers directly to miles if you know that conversion. If you don't, then I'd probably go meters, then meters to miles. Okay, it's up to you. 1 kilometer is 1,000 meters. Do we know how many meters are in a mile? Like track people? 1,600, right? That's a close enough conversion for us to count it good. Right? It's technically 1,609, but I don't care. Okay, it's close enough. So 1,600 meters is in a mile. Okay, so I need my calculator for this one. 2 point... That gives me 1.52 miles. If I'm looking at sig figs, I might technically want to throw one more digit on there. 1.521. Okay. Questions? Why don't you try this next one on your own here? How many seconds are in a leap year? What do we have to know first? What do we have to know about a leap year? We need to know how many days are in a leap year. 366. Mm-hmm.
Oh, there's an extra.
Normal's 365. Yep.
I thought it was an extra.
Mm-hmm.
I thought it was minus.
So we're going to start with days and then work our way to seconds. So go ahead and I'll give you a jump start here.
No.
But do we know, do we start from days?
Start from days. Yep. And you don't, do we need to bother going to months?
No.
I don't think so. Just go days to hours, minutes, seconds. Right? Or hours to seconds if you want. Is the expectation here that we have a really big number or a really small number? Really big, right? We should be thinking about that. So I got something in that range. 31,622,400 seconds. Are we okay with where that came from? 60 minutes times 60 seconds, right? I just took one step out of my chart. You could work it all the way out if you want. You don't have to. Okay, the last little conversion I want to show you today is this conversion right here, okay? Meters per second. Any idea what the unit meters per second would represent? Speed, right? Speed, how fast something is traveling, how many meters it's going per second. So that's representing speed or velocity. And so we're going to convert this a little bit differently. When we start our T-chart here, we're going to say 1.3 meters per second, right? Because what does per mean? It means divide by, right? It's this many meters over 1 second. Okay, and since it's a 1 there, we don't have to write the 1, but we're saying our object is traveling 1.3 meters every 1 second that goes by. So when we do the conversion, we can't say this, 1.3 meters per second, and do our conversion like that. It doesn't work, right? So it has to be meters per second. And so now when we walk the conversion out, we're going to convert meters to probably to feet, and then feet to miles. You could go directly meters to miles if you wanted to with our 1600, right? And so now, right now, if I stopped my conversion, I would be in miles per second, which is not what I want. I want to go miles per hour, which means to get rid of seconds, I need to bring it up. Up until this point, everything we've done is to cancel downward, but realistically, we need them opposite. So if seconds is in the denominator, now it's going to be in the numerator, seconds to hours. Okay, so now I can go fill in my numbers. And sorry, I took that one extra step, but all right, so meters to feet. 1 meter is 3.28 feet. 1 mile is, do we know? How many feet? 5,280, good. And then 1 hour is equal to 3,600 seconds. Okay, so our process is multiply across the whole top, divide by the whole bottom. And so that gives me a value of about 2.9. Is that what we had? Miles per hour. 2.9 miles per hour. Okay. So I wanted you to see that type of conversion here, because when we do these velocity or acceleration or whatever types of conversions, we have to make sure that we're using that per, right, as our fraction. Okay. All right.